and let me
Super
get the
quick,
screen
Lisa.
share.
I have
I'm
a
sorry?
quick question.
Sure.
Quick question for you. I was in Linquist today, and because I brave the face-to-face teaching world, and I saw on the announcement board that you received a really big grant.
I am part of a really big grant, I would
Okay, well,
say.
congratulations.
Thanks. I think it was a slow news day. Like they were out of positive things to say, and so that grant got way more press than it should have. But thank you. I am co-PI on an IES project that was finally funded after about 5 years of trying. So there's the backstory that you don't get to hear is that it took multiple submissions, and we finally convinced them. So hooray on that. But yes,
Congratulations. There's a
thank you.
really nice big picture of you on all of the monitors in
Oh
Linquist.
no, I'm so glad I'm not there to see it. It's probably the one they forced me to take last fall. Because when I was new faculty, they were like, you have to take a new picture. I'm like, can't I just use the one that's 10 years old that I've been using for a while? Yeah, ironically, they made me take a new picture, and then I tried to put the picture up into my faculty page, and they told me that I couldn't because it had to be an indoor picture, not an outdoor picture. And so I said, okay, we're sticking with the picture taken at Sears in roughly 2009. So yes, if you're wondering why my hair looks a bit different, I was rocking a different highlighted hairstyle back then, but I figured this is close enough for government work, right? Which is I'm a government employee. So anyway, so thank you for that. I'm extra glad I'm not in the building anymore, as it were, so I don't have to encounter that. Okay, so you should all be able to see my website, the class website. Got the stuff on here. I think I gave you yeah, I sent a few things out in announcements via email, but just to make sure that we're all on the same page. It looks like everybody was able to complete homework 0, so you all have 3 points of extra credit to start off the semester. Inside the homework portal, right now you still have a grade of 0 because the extra credit points go into the numerator and the denominator is still 0, so you can't divide by 0. So everybody has a 0 because nothing else has been due, but you have that completed. Homework 1 is up, and looks like some folks have already gotten started on it. Please let me know if you are running into problems fighting with SAS or Stata, getting it to figure out where your files are, or if you get stuck on anything else. I'm happy to help. I do have office hours today, 3:15 to 4:45, Tuesdays and Thursdays as usual, and I am available at other times for individual meetings if those times don't work for you. I also posted your first formative assessment, which is available under quizzes in Icon. And as a reminder, those are not graded. They're just opportunities for you to review, make sure that you're following sort of the big picture of what's going on. And I do need to explain a little bit of background for the last question. So the last question on there asks you what your theme song would be. So picture if you were a professional athlete, right? And it's your turn to participate. So you're going up to bat in baseball, or you're coming off the bench in football or basketball or soccer or football, as it were. What would be the song filling the arena, right, that welcomes you? That's what I want to know. It can be any language. I'm always looking for cool new music to run to. So if you wouldn't mind sharing a YouTube link so I could check it out, I would appreciate that. I would say that there are no incorrect answers, but actually, one time someone told me that Christmas music was their theme song. And I said, I'm sorry, no, I can't accept that. That is, in fact, incorrect. Jingle Bells is not a theme song. That is no. But other than that, if you wouldn't mind sharing, that gives me a chance to get to know you guys a little bit more. So all right. Any questions on any of that or other logistical kinds of stuff? No. Okay. Question from the audience. Any preferred genre for running music? Honestly, anything that has a good tempo. I have stuff ranging all the way, I would say on my iPod, but it's actually an MP3 player that's about 12 years old that hasn't died yet. So I'm old school. When I first started running in junior high, I carried a Walkman that played tapes like in my right hand. And it went from a Walkman to like a mini disc player, and now I have an MP3 player that I carry in my right hand. But always, forever, I will carry my music in my right hand. And so that has stuff all the way from, I'd say, the 70s up to I have like a little bit of Lady Gaga and that's about as recent as I get. I'm not so much with the new music. I'm too old for that. So especially if you have cool new music to use as your theme song, I would not have seen that before. Odds are good. So feel free to share that. Um, all right. So any other questions, logistics stuff, anything like that? No. Okay, I'm still here, right? No freezing yet? Okay, you guys are here. All right, excellent. Thank you for being here. If I haven't said that already, it makes it so much more entertaining to do this than to just talk to a computer. I have, let's see, lecture one pulled up here. So starting on slide 27, thought it might be good to do a little bit of review before jumping into the parts that we haven't finished. So what we're covering right here is in the second half of your first homework. So you should be able to do everything through section one. And I hope to be able to finish most of what is needed for your homework today. If not, if we have to stretch into next week because of losing Tuesday, then I will bump the due date back 2 days to compensate. So don't worry if we don't get everything done. That's okay. So we were talking last time about extending univariate statistics. So the idea of describing a variable in one sample into how do we use that information to make some sort of statement about how that sample compares to our hypothetical population. So making inferences is the key here. And two different instances of inferences that one would want to make about a single variable is to be able to compute what is known as a confidence interval. So that's the first part here. How unexpected, how discrepant would the sample statistic be across repeated samples? So the sample statistic could be any number that you're computing to describe a variable. So we're going to talk a lot about the sample mean because that's the easiest case, but the same ideas hold for other sample statistics. So if you wanted to talk about how skewed your variable was and how that estimate of skewness would be likely to be found differently across other samples, you could compute a confidence interval around that. So just know that any quantity that's summarizing your data for one variable, you can compute indices of inconsistency, is what we're talking about, how much it would vary across samples. So confidence interval is one. That's going to be an expected range in which your an expected range that should contain the population version of your statistic, as well as to compare your sample to some sort of known population value. So you can think of this maybe in the context of representation. Like if you know that the population has this characteristic, X% of your population belongs to this group, for instance, and you have a sample that has, Y%, is that close enough? Or is that reason to be concerned that your sample doesn't adequately represent the population? So going from one sample to what would it look like across samples? That's what we're trying to do. Okay, with me so far? All right, excellent. So we went over this last time, but I'm going to go ahead and assume since that was like a full week ago that it's not fresh at the top of your heads anymore. Is that a reasonable assumption? Maybe a little bit of review would be good. At the very least, if you do remember this, then you can feel good about having that win. Like, yeah, I got this. I got this. So I have here fake data. So I generated this to make a point. So this is for demonstration purposes. I generated a variable for 100,000 fake people. That's my population. And I know that because I made this data, that the mean of the population is 10 and the variance of this quantitative variable is 25. So variance is in a squared metric. If we unsquare variance, if we take the square root of it, then that becomes standard deviation. Standard deviation tells you how far off any one person is from the sample mean. So it's an index of discrepancy within a sample, how different people are from each other. How far off on average from the sample mean? That's standard deviation. So in this case, people would be expected to be off by 5 on average. And this particular shape was generated by what's known as a normal distribution. We'll see a lot of instances of that. So if I wanted to talk about how likely any one sample is to give me back that right answer with respect to the population mean, I can do that by doing simulation. So these pictures right here were generated by a repeated process of grabbing a sample, calculating the mean, storing that mean, grabbing another sample, calculating the mean, storing the mean, and what I varied was how big the samples were. So that repetitive process was done 1,000 times in each of these boxes here, but the boxes differ in how many people were inside each of the gathered samples. And so what this is designed to illustrate is that the more people that you have, the closer any one sample's mean is going to be to the population mean. So all of these, we'll call them piles. Does that work for a descriptor? All of these sort of mounds of data. These things are displaying the sampling distribution of the mean. It's what would the mean look like across varying samples of the same kind, where kind in this case is the same type of variable and the same sample size. And so if you look at the samples of 5 people, any one sample is going to have a mean that's more different than the population mean when there's only 5 people than when there's 50 people. So they get tighter. And these sampling distributions get to look more normal. They get more towards a normal distribution in shape. And so this helps us to quantify how inconsistent any one sample would be relative to where it's supposed to be on the population mean. This idea of a sampling distribution of the mean we have in fake data. We don't have it in real data because we only have one sample. But because of math, we have found a way to approximate this column on the right here. So this is giving you the standard deviation in these little distributions. In this case, it's how far off on average any one sample's mean is from the population mean. So it's supposed to be 10, but any one sample, how far off is that going to be? If there's only 5 people, it's going to be off by about 2.2 on average. But if I've got 50 people, the sample mean is going to be off from the population mean by only 0.7. So this column right here that we can actually see in my fake data is going to be approximated by something called a standard error, the standard error of the mean. So what goes into standard error are 2 quantities. One of them is sample size. So as you get more and more people in a sample, the wiggle of the sample means around the population mean, the width of these mounds shrinks. So you have more people, less wiggle, more precision, less error. The other thing that matters is how discrepant the people are from each other in your variable. So I generated another faked set of 100,000 people, this time from a distribution with a standard deviation of 3 instead of 5. So the people are packed more tightly together. Any one person is likely to be off from the mean of 10 by 3 on average instead of 5 on average. And so that's why the distribution looks taller and more squished together. Well, if I do that same sort of repetitive process, we see that the distribution of the sample means, so the same process of going into my 100,000 people pile and extracting samples of different sizes, the same thing happens that we have tighter distributions with more people. But if we compare the two, we see that the distributions are even tighter when the standard deviation of one person from the sample mean is only 3 relative to when it's 5. So more people means less variability from one sample to another, and smaller standard deviations means less variability from one sample to the other. So we can call it, they work in opposition. So where we're headed to is this little formula right here, standard error of the mean. That's something that we can compute with only one sample. And yet, because smart people figured this out a long time ago, we know that it's going to reasonably approximate what it would look like if we had all the samples and we could talk about the wiggle from one sample to the next. So standard error of the mean, in this case, since the mean is what we're focusing on, is the standard deviation of the population divided by the square root of sample size. So more spread in the variable means more wiggle from sample to sample, and fewer people in the sample means more wiggle. In practice, we don't know what the population standard deviation actually is like ever, right? This is one of these textbook examples that doesn't have an analog to real life very often. So we use the sample standard deviation instead. So we substitute this thing right here. Does anyone remember what this little letter is called? The little circle with the tail on it?
Sigma.
Sigma, yes, lowercase sigma. Big sigma is like a meh, I can't do. I need three hands to do a big sigma. But yes, there you go. That thing. We've seen one of those before, but this is lowercase sigma. So sigma is the notation for population standard deviation. We use S, just a regular letter S for that for sample. So because we're substituting what is supposed to be truth with what we have as a guess using one sample, we got to deal with that. That's coming today. We haven't started talking about that yet. So standard deviation, standard error. These are two different things, even though they sound the same. Standard deviation leads to standard error, but standard deviation refers to one variable. It refers to how far off any one person is from the sample's mean. Standard error refers to differences between samples, not people, samples. Standard error is how far off any one sample's mean is from the population mean. And we can compute that even though we only have one sample using that sample's standard deviation and its sample size. And if you compare what happened in the simulated data where I was actually able to observe the differences between samples and what the mean ended up being, that column of standard deviation for the mean, y bar in this case is the sample mean, this is what the standard error would be if I computed it with the population standard deviation, which I know, versus the sample. And if you have enough people, it starts to get down to here 20, 30 people. It doesn't make a difference, and these line up pretty close. So any one sample's standard error computed as its standard deviation over square root of sample size is an approximation for how wiggly your sample mean would be across samples. It's going to be underestimated in smaller samples if you use the sample version of the standard deviation rather than the population. So we're going to have to do something to adjust for that. That's what's coming next. Okay, so with me so far? All right, any of that you want to hear again or hear differently? Cheers. No, we're good? Okay. So this idea that the distribution across sample means becomes more normal as you get more people in each sample, that's called the central limit theorem. We looked at this last time, I believe, too, just to demonstrate that it still holds even if the variable that you are starting with is not normally distributed. So central limit theorem is not about each variable having a normal distribution. It's about the distribution of the means across samples having a normal distribution. So here's a count variable. I generated this using what's known as a Poisson distribution. It has a mean of 2 and a variance of 2. And if I do that same resampling process, you see the same tendencies where the more people per sample, the closer together the sample means get, the less wiggle that they have. And the standard error within each sample if we take the average of those, it reasonably approximates the standard deviation of the sampling distribution. So it works even if the variable itself is not normal. So any statistic has a standard error to it. It's not always easy to compute. The mean is one case in which it is easy to compute and it works out that it's normal or close to it in almost every case. And so that's a good way to get started on this concept. We're going to use the standard error to do two different things. One is to characterize the range of uncertainty of what the sample mean would be across samples and how likely it is that the population mean would be inside that range. And in order to do that, we need to have two things. We need to be able to decide what a good shape would be to describe the sampling distribution of that statistic. For the mean, we can go with normal. And we need to decide how wrong we're willing to be. And so you can think of this in opposing sets of vocabulary. So if you describe confidence limit or confidence interval, those terms are synonymous. That's like how right you want to be. The opposite of that, one minus that, how wrong you're willing to be, is alpha level. I just got the dreaded unstable thing. Am I back? I'm back? Okay, excellent. So here's our friend normal distribution. This is what we're going to use to provide a basis for the range of expected differences across samples in their mean. But we're going to use a particular version of it that puts all of the variables onto the same scale. So it doesn't help to have a normal distribution that takes a particular mean and a particular variance because that won't work for all problems. What we need to do is take what's known as a standardized version of that. And so a version of this that has a mean of 0 and a standard deviation of 1 or a variance of 1 creates a new standard normal distribution. And this thing is, you will see this all the time. If you haven't seen it already, welcome to standard normal. So the variable that's on the x-axis in this picture is z. So z in this case is what values of this distribution are called. And the purpose of any distribution is to tell you how likely any one score is for a variable that is generated using that distribution. So in this case, we're assuming that this distribution describes the differences between samples in their means. And within one standard deviation around the mean is expected to be about 68% of the data. 95% of the data is within about 2 and 99% within about 3. And so that's where these different choices for how wide your expected range should be come from. So what we're going to be computing is what's known as a confidence interval. The numbers that go into that computation come from this distribution. So a confidence interval, I have the text coming up on the next page here, I think, but just to give you a preview, it is the range in which the expected population parameter should fall that percent of the time. So you can think of it as like, I have a sample mean, the sample mean is 8, let's say. How wiggly would that sample mean be across samples of the same kind? The range describes the extent of wiggle. And so how precise you want to be is a choice that you can make. These are very common choices. 95% is probably the most common. So we can use that choice. Excuse me. Why does it always do this? I have there's one little thing that keeps getting out of whack on my slide and it's driving me nuts because I can't figure out why it keeps doing this. But every time I pull up this right here, it gets centered instead of left aligned. There. Now you can see it a little better. Let's hope it stays. And it goes back. Oh, okay. Phew. Gonna lose my mind. PowerPoint is gonna make me lose my mind. All right, in a bad way. Here we go. So let's say that I want to talk about a confidence interval for one sample. So out of my original fake data, 100,000 fake people, normally distributed variable with a mean of 10 and a standard deviation of 5, I take one sample. And I draw one sample of 50 people. And for that sample, here's what I get. I get the sample mean. So this thing that I'm pointing to here, y bar, is how we indicate the sample's mean. It works out to be 10.98. So that is our estimate of the mean. That's our best guess as to what the sample mean would be. I'm highlighting the word estimate here. An estimate can be something that is computed, or it can be something that is found through an iterative algorithm. Not all computations are possible to be done by hand in statistics. So whatever answer is like the best version, your most likely answer, you can think of that as the estimate. For something like the sample mean, we don't have to do anything fancy to get it. We just compute the mean as normal. Likewise, we can compute the standard deviation as normal. So the sample standard deviation is 4.6. So relative to the population that it's supposed to be, this one sample has a mean that's a little bit high and a standard deviation that's a little bit low. So we don't expect to get the right answer every time we take a sample, but we expect that if you average across them, you get back to the right answer. So I can use that sample standard deviation. So 4.6, that is telling me that any one person is going to be off from that sample mean of 10.98 by about 4.6 on average. So that's within a sample, those two numbers are talking about the discrepancy across individuals. I can then compute the standard error of the mean that takes that standard deviation across individuals, divide by the square root of the sample size, and that works out to be 0.65. So 0.65 is telling me that my sample mean, not my sample mean, any sample mean is expected to be off from the population mean by about 0.65. On average, any one sample is going to be off from the mean of 10 by 0.65. So if I look at my sample mean is a little bit more off than expected because it's off by 0.98 relative to the 10 that it's supposed to be. I can compute for my one sample mean a confidence interval. And the basic formula of a confidence interval is right here. It's what is the thing you're computing the interval for? That's your estimate. In this case, it's the sample mean that we want the interval for. Later in the semester, we will compute intervals for intercepts and slopes from models as well. So what is the thing we want the interval for? That's the estimate, that's in the middle. Then plus or minus around it is some critical value that gives you the area that is expected to correspond to the boundaries of what is expected versus unexpected, and then the standard error that defines how wide that your interval should be. So here's 3 different confidence intervals, all using the same information. So the middle of each of these intervals is 10.98 because that's my sample's mean. The width of the interval is going to be a function of its standard error. So how far off from the mean you are on average, how far off any sample's mean is from the population mean on average. That's my standard error of 0.65. And the parts in color here, those correspond to the areas under the normal distribution. So the first one gives me a 90% confidence interval. So 9.90 to 12.05. So when you're reporting this information, 9.90 would be considered the lower bound, homework question, and 12.05 would be the upper bound. You can use the term lower and upper boundary or interval or level. Like you see lots of word salad with these. They all kind of mean the same thing. But what this is telling me is that 90% of my samples would be expected to contain a population mean somewhere between here and here. The population mean is going to be in my interval 90% of the time. If I want it to be 95% of the time, the interval needs to get bigger. And if I want it to be 99% of the time, it needs to get even bigger. So this is the interval that is expected to contain the population version of that statistic, the mean in this case, that percent of the time. So we can then, let me hold on that. I'll show you a demonstration of that in just one. If you want to describe sort of the variability across samples in the mean, the confidence interval gives you that. It's an index of wiggliness, right? If you want to compare your one sample back to the population mean it's supposed to be, we can also do that. And that's the next thing that I have here is using the same sort of information in a different way. So let me pause, reload the caffeine, and see if there's questions. All right, are you with me then? There's no questions? Still awake? Still awake? I know it's the after lunch slump. Making sense so far. Excellent. That's all I can hope for. So this one sample, right? I know what the right answer is because I made up the fake data. The right answer is 10. And my one sample that I pulled from my fake data is 10.98. Is that off in a concerning way, like something is wrong? Or is that off in like, well, there's going to be some wiggle and it's fine? Let's find out. So if I want to answer that question, how does my sample compare to what it's supposed to be in the population? This presupposes that you have an answer to what supposed to be is, by the way. So you're comparing your sample to some sort of known or accepted standard. In this case, I've got fake data, so I can do that. I'll show you a real life example from a publication where we had something analogous using real data. But we can compute what is known as a one sample z-test to try to answer that question. If the right answer is 10, but my sample mean is 10.98, how far off is that? Like, is that problematically off, or is that off within some sort of expected range, expected wiggle, as it were? So what this is doing is creating what's known as a test statistic. That's a mouthful. We're going to have 4 different test statistics this semester: Z, T, chi-square, and F. That's it. Here's your first one. Welcome to Z. So this is where notation, remember I warned you this is like learning a new language, right? So in words, Z is my test statistic, is computed as y bar, that's my sample mean, 10.98 in the current example, minus U looking thing, what's that? What's the U looking thing called? What's the name of it?
You, right?
Yeah, mu. Yeah, mu, the Greek letter. U looking thing is what I tend to refer to it as. It's U with an extra tail on the front. Uh-oh, I've made my computer angry. I'm getting a giant pink hourglass on my monitor. That can't be good, but we'll find out that's unhappy about in just a moment. And then divided by the standard error of the mean. So we are translating our observed and expected onto a standardized space where we can say, given this value, yes, this is expected, or no, this is unexpected. So if I work out the math, I end up with a z-test statistic of 1.5. Okay, what the hell is that? Glad you asked. Here's a picture. So if I have my standard normal distribution where the mean is 0 and the standard deviation is 1, what I have done is mapped my result onto this distribution where the mean of 0 corresponds to what is expected And expected in this case is my population mean of 10 that I know to be true. Expected wiggle, right? How far off? That's given to me by my standard error, which is 0.65 in this case. So relative to expected in this standardized space, my samples mean of 10.98 corresponds to a z-test statistic, a z-score in this case, of 1.5. To the best of my PowerPoint drawing abilities, this is 1.5. Okay, close enough, right? So under the standard normal distribution, I know, because calculus, because people smarter than me figured this out a long time ago, so we can just say we know, that 93% of the time we would see a result that is less than what we found, less than 10.98, and 6.7% of the time we would see a result that is even more extreme. So this tells us this z-test statistic is mapping us into a space where we can decide what is too extreme relative to what is expected. So this is simply telling me that if the population mean were 10, which I know it is because I made up the data, I would see a mean higher than 10.98 about 7% of the time. I would see a mean of 10.98 or lower 93% of the time. So said another way, our observed result, our z standardized version of the difference between our sample mean and the expected population mean, is 1.5 standard errors away from the expected mean. 1.5 standard errors is what a z-score of 1.5 means. So what we would do in practice is decide ahead of time how far out we're willing to go before we say that this is unexpected. And that idea corresponds exactly to the idea of the confidence limits that we talked about just a minute ago. So we have a sampling distribution that describes the expected behavior across samples. It's normal for now. We're going to meet another one in a minute, but it's normal for now. And we need to decide, where does unexpected begin? So there was a question like last week, I think, and I forget who asked me it, I apologize, as to whether or not there's like a cutoff for what is a good standard error versus bad. Now we're talking cutoff, right? A standard error is used to place us onto the standardized space that we are going to put a cutoff on. And you have to decide how far out into this shape is too far out. How infrequent is too infrequent? And so the idea of what is the level of unexpected that you're willing to accept is alpha level. It's the opposite of confidence level. And if you want to be 95% confident, your alpha level is 5%. If you want to be 90% confident, your alpha level is 10%. So you only need one or the other. You will see, for instance, in SAS, it wants you to specify things in terms of alpha level, whereas Stata wants you to specify things in terms of confidence level. Why? I don't know. They just like to do things to make it harder, right? I think of it as job security, right? Because if you learn these little tricks of the programs and how things are all kind of really the same, but just enough different to be confusing, someone will pay you because they don't want to have to figure this out for themselves. So alpha versus confidence, same concept, different ways of approaching it. So alpha equals 0.05 is sort of the universal standard that people have decided on a long time ago. And the other thing that you need to ask yourself is whether or not you're willing to accept an unexpected result in either direction. Almost always the answer is yes. If you're willing to say, I understand that my sample mean could either be too high or it could be too low, and I'm willing to say unexpected exists in either direction, that's what's known as a two-tailed hypothesis test. Either side. If you're willing to put all of your eggs in one basket, so to speak, and say, no, 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 I only care about one of the ways that it could be unexpected, that is a one-tailed test. And I have gotten into arguments with other people on Facebook about this, but I claim that one-tailed tests are bullshit voodoo. That is my professional opinion, bullshit voodoo. In my professional opinion, they are only appropriate when when the other side is impossible. So let me give you the only instance I can think of in which that is true. Remember variance? Remember what variance is? Like this sort of how wide your distribution is? What is the smallest number that variance can be? Oh, we got one answer. Yes, this is another one we can do hand signals. 0, right? If everybody gave you the exact same answer in your sample, then your variable is actually a constant. It has no variance. Everyone agrees. Homework question. So variance can't be below 0. Okay, stream is back on. Am I back?
We lost you at about the variance cannot be below 0.
Okay, yes, variance can't be below 0. So either in later instances of statistics, one of the hypotheses that you may test is whether or not a variance is different than 0. Like whether there exists variability because of a certain source of sampling. As a practical example, let's say that you are doing qualitative coding and you want to compute reliability across your raters. So how much do people who are looking at the same pile of data come to the same conclusions, right? Ideally, you don't want any variability across your raters. You want them to agree 100% and have perfect reliability, perfect agreement. So you may be in a situation where you have to test whether or not there's variance across your raters and you're testing it against 0. Well, because variance can't be below 0, the only thing it can be is above 0. So that idea of you can only have more than 0 but not less, that would correspond to a legit one-tailed test. But in most cases, you can have a result that is too low or too high. That should be a two-tailed test. So what does the difference look like? We'll have pictures of that in just a moment. But what I'm talking about, more generally, is known as null hypothesis significance testing. That's a mouthful. And it's also easy to get confused as to what null means. So a hypothesis is just a statement about a population parameter that you are trying to make guesses about using the data that you have, the sample data that you have. Null hypothesis, and so you are going to see this throughout this course, it is abbreviated HO. I don't know why, it just is. H for hypothesis, 0 for null, but this is where it gets confusing. The null hypothesis is not necessarily saying that something is 0. The null hypothesis is whatever you expect something to be. So in this context, I know because I made up the data that the population mean is 10. That's my null hypothesis. That is what any one sample's mean is supposed to be because it came from a population with a mean of 10. So a null hypothesis just sets up what is expected. What should have happened? Alternative hypothesis then is, okay, if that didn't happen, what could have happened? And so the idea that you would have a mean that is different than the population mean, either too high or too low, that corresponds to a two-tailed test would be written like this right here. Mu is not equal to 10, or in Stata, it looks like this in the output. It's equal sign with an exclamation point, meaning different than. So if I believe that something should be 10 in reality, in the population, and I have a sample mean, I want to test how likely it is that how likely that mean is to have been observed if the true mean were 10. Is it too high or too low? That's a two-tailed test, which means that I have to divide up my likeliness areas into two sections. So here's some pictures. Pictures help with this, I think, usually. Am I still together with you guys? No, internet still cooperating? All right, all right. So pretty pictures here. So let's see what we could have said about different decisions given data. So if what I expect is a sample mean of 10, and I have declared ahead of time my probability of where unexpected begins in comparing any one sample to that population mean, meaning that my alpha is 0.05. So if alpha unexpected, the way to remember that, by the way, a mnemonic is alpha means aberrant. Alpha unexpected, aberrant means not likely to happen very often if this were actually the case. So 95% expected, 5% alpha unexpected, aberrant. Here's two different ways of looking at what could happen. So under green here, so look at the green parts of the picture. If your alternative hypothesis is that your mean is greater than the 10 it's supposed to be, then your critical point on this standard normal distribution, where the dividing line of 10% of the time it would happen is, corresponds to this x-axis z of 1.65. So we would say that any sample mean that is greater than a z-score of 1.65 would happen only 5% of the time. So if we're in this other side, we would call that 95% of the time expected, meaning it's 10 or close enough, because we're completely disregarding the chance that it could be way less than 10. We're putting all of our eggs onto the positive side. We expect 10 to be greater. So when would this be a problem? Well, what if we were looking at something like mean effectiveness of a drug to say, I don't know, cure a pandemic? Just a hypothetical example. And what if you found out that this drug didn't make people better? Right? We had a hypothesis that relative to leaving people alone to die, this drug should make them better. That's a positive direction. Well, that could mean that they were not better enough, meaning that they didn't cross into this magical green dividing line to get to the 5%. They might have been just over here. Or they could be all the way over here where it actually made them worse, less than expected. So to me, this is why one-tailed tests are bullshit voodoo, as I said earlier, because it's misleading if you actually made someone worse to say, no, they're not better. They're not better. That's not the same thing. The opposite direction is illustrated by the pink, where you had a hypothesis that you should be less than 10. And you'll be putting all of your area into where unexpected starts on this side. And if you actually had a result that was greater than 10, you're just saying it's the same as not being, as it's within expected territory. You don't care. So in this class, at least, we're not going to be dealing with one-tailed tests ever again. But because they do occasionally come up, I think you have to have a very strong theoretical justification to do them for a statistic that could be high or low, but that's neither here nor there. I wanted to make sure I've covered that. So question from the audience, could doing one-tailed tests protect against errors? I don't think so. It would make type 1 error more likely if you used a one-tailed test to sort of load all your area in one direction. In theory, I guess type 2 errors, it could make better, but that's still not a reason to do it. Those are concepts that we'll be getting to at the end of either this lecture or the next one, type 1 and type 2 errors. So I'll put a pin in that because we are going to get there. So if we're unwilling to say that only one side of this matters, if we're willing to say our result could be too high or too low, because you're supposed to decide this stuff ahead of time, then this is what it would look like. So back to our one sample. It comes from a distribution where the mean is 10. So that's what is expected. That is my null hypothesis. And I am willing to say that any one sample's mean could be too high or it could be too low. So where unexpected is has to be in both sides of the distribution. Then I am defining a priori my hypothesis space to be this blue section here. So where 2.5% on either side, where that starts, corresponds to a z-score of 1.96. So an alpha of 0.05 means that if the null hypothesis were really true, we would see an extreme result due to just wiggle, due to just expected fluctuation across samples, less than 5% of the time. So too weird starts at 5%. And because too weird could be too high or too low, it's 2.5% in each corner. So that's our magical cutoff that we're deciding to make this black and white statement as to whether or not what we've seen in our sample is too weird or within expected fluctuation. So our sample, what did we get? Well, our mean was a little high. It was 10.98 rather than 10 it was supposed to be. Given the standard deviation that we observed within our sample, we get a standard error of the mean of 0.65. Our result corresponds to a z of 1.5. So that's like saying we're 1.5 standard errors above the mean. Our result of 1.5 is right here. It doesn't meet the cutoff for unexpected. So what we would conclude is that our mean of 10.98 is not unexpected, right? It's within the area, it's within the 95% that would be described by just your average expected bounce, fluctuation, wiggle around the mean. If I were to compute a confidence interval around my mean, so I'm using the 1.96 in the interval that corresponds to this demarcation as to where unexpected starts, then that confidence interval is 9.7 to 12.25. So you'll note that the expected mean is within the interval. So that's another way of saying the same thing. If the confidence interval around the mean contains the population mean, then what you have is not unexpected. It's expected. I'll say that again. If the confidence interval that you compute around your mean has the population mean in it, then your sample, it just has expected fluctuation. So we know.
Guys, I'm in class. Go downstairs. Go downstairs.
Yes, parenting interrupting. No worries. So we can further clarify how unexpected this would be. And this is where our friends SAS, Stata, R, SPSS, and other packages will do this for you. I promised no looking up tables in the back of the book, and I meant it. It works out that a z value of 1.5, so a sample mean that is 1.5 standard errors above the population mean, would be expected 6.68% of the time. So a result higher than what we got would be expected 6.68%. A result lower than what we got would be this whole 93%. But if we want to divide it into more extreme, then it's 6.68 on either side. So putting it together, what this Z thing is doing is placing your comparison of your sample mean to the population mean it's supposed to be, the null hypothesis it's supposed to be, onto a standardized space where we can say that anything in this space past this cut point is unexpected and anything within these cut points is expected. and you decide a priori where you want to put the cut points. If you want to say 95% is expected territory, it's a z of 1.96. If you want to say that only 90% is expected and you're willing to expand what you consider unexpected to be more lenient, that would be a z of 1.65, if I remember correctly. Okay. How are we doing? Ish. Okay. So this is, I warned you, it's notation and vocabulary and logic. The math is straightforward. The math right now is fairly straightforward and the computer will do it for you. It's hanging on to the logic is the hard part. We're trying to make an inference from the one set of data that we have, right? We've got one sample and we're using magic and calculus and statistics, some combination thereof, right, to extrapolate how that one sample would compare to the population that we believe to be true but don't necessarily have. In my example, I've got the population so I can show you whether or not this works. In real life, we don't know what the population is, but this test is only useful to you if you have a population estimate that you know or that you're willing to say is true enough. So examples from stats textbooks would be things like this. This can is supposed to hold 12 ounces. That's my population. That's what it's supposed to hold. That's my null hypothesis. If you have a standardized test score, a lot of tests are normed so that the mean is 100 and the standard deviation is 15, say. Then that's your population. That's your null hypothesis. So I'm using this not because it's super frequent in research, but it's a way to get you used to this sort of decision logic of deciding whether or not what you found is unexpected relative to some kind of expectation. So to put more words on this, so confidence level, expected. Alpha level is the part that's unexpected or aberrant. So we're doing what's called more informally a significance test. And so I want to attach the words significant and not significant to these sets of decisions. So if your test statistic, like Z, exceeds the benchmark for where you've decided unexpected starts. So this one instance, unexpected starts at a Z of 1.96. If you have a result that's further out than that, it is larger than 1.96 or smaller than negative 1.96 because you're willing to say either side matters, the p-value that you get, the probability of observing what you found in your sample if the null hypothesis were true. That's what a p-value means. And P stands for probability. It goes back to these areas. The blue here is saying that anything outside this blue box would happen less than 5% of the time. Probability less than 5% of 0.05. That's what alpha is referring to. So if you are outside of that blue box, if you have a result that is deemed unexpected, the test statistic that you find exceeds the boundaries that you set up to where unexpected starts, the language that goes with that is that you reject the null hypothesis. In other words, more plainly, you would say the result is significant. Now, significant is a very special word. This is not something to where you can say a synonym and have people know what you're talking about. Statistically significant has a very specialized meaning. It means that what you found is sufficiently unexpected given the decision rules that you set up in advance. It's weird. It's beyond what would be expected for normal wiggle or fluctuation. It's aberrant. it would happen less than 5% of the time if that's where you decided unexpected starts. So you're saying, I reject the null hypothesis. My result is too far out for the null hypothesis to be plausible. My sample is weird. And you would call that result significant, statistically significant. So what happened in our case? We didn't hit the threshold. So our sample mean of 10.98 was different from the population mean by a standardized score of 1.5. Our z-test statistic was 1.5 standard errors away. That doesn't hit the cutoff because 1.96 was the cutoff. So we're inside the expected range. This is a mouthful. The way that you would describe that is that you do not reject the null hypothesis. And you would look at that and think, can I just say that I accept it? And someone will yell. They will yell loudly. Reviewer 3 will lose their damn mind if you ever say accept the null hypothesis. That's what will happen. You are not ever allowed to say that. Someone will yell. Even though it kind of sounds the same. The reason is because given enough data, the null hypothesis is always going to be rejected. So it's more of a philosophical distinction. Here's another thing where people will agree to disagree. I think it is acceptable to say that you retain the null. Do not reject and retain to me are both okay. Other people would lose their minds at that. In practice, people don't talk like this. Like this is language that goes with stats classes only. What people would say is that your result is non-significant. Non-significant or not significant. You can say either of those. So in our example, our sample mean of 10.98, because its z-test statistic of 1.5 did not cross into unexpected territory, it's within the bulk of the box, the blue, our sample mean is not significantly different than the expected mean of 10. That's what I would say. Another thing that you will get yelled at for is if you say insignificant. That is not an acceptable synonym. That is a value judgment. Insignificant is like, who the hell cares? Not significant means within expected territory. I bet you never guessed there'd be such passion involved in numbers, right? People take this shit seriously. They totally do. So mapping all of this back together. Okay, I have a sample mean of 10.98. It was supposed to be 10. Close enough? Eh. Well, what's going to determine whether or not it's close enough? Two things. How many people were in my sample and how variable those people were. Because how many people were in my sample, n, and how variable those people were, standard deviation, that gives me standard error. And so that helps map my sample's result onto a broader collection of hypothetical samples. So my test statistic, which is the sample mean minus the population mean divided by the standard error, that test statistic is 1.5. That corresponds to a p-value of a probability of 13.36%, a p-value of 0.1336. And in your output, this is the information that you will get. It will tell you what z is and it will tell you what p is. What that information then means is on you. So what that is telling me is that I would have found a sample mean as different or more different than the expected 10 that it should have been 13% of the time. And it should have been, if I wanted to call this too weird starts at 5% of the time. So my result is not weird enough to be flagged as unexpected. 1.5 standard errors is within expected territory. So even though I know that what happened is that my mean was too high, I have to talk about it as if it is either too high or too low, because a priori I decided to accept the possibility that I could be off in either direction, a two-tailed test. So putting it together, I would say that my sample mean is non-significantly greater than the expected population mean. So these will be more homework questions, and everything that I give you, there's going to be a direction and there's going to be a declaration of significance. Direction is going to be given by the test statistic in most cases. So Z is positive, which means that my sample mean is above expected population mean. If my sample mean were below, then Z would be negative. And I can also just look at the numbers, right? 10.98 is more than 10. 10.98 is greater than 10. Whether or not it's significantly greater, whether or not I reject the null hypothesis, has to do with how many standard errors away from the mean it is, and whether it's enough to head into unexpected territory. And with a decision rule of 5% is where unexpected starts, 2.5% on each side, it doesn't hit it. So it's non-significantly greater. If I had more people, or if I had less variable people, it might have hit it. If the standard error were smaller, it makes it easier to claim that it's unexpected. All right.
I'm sorry, Lisa, could you just explain one more time? You said there were two things it depends on. One is direction, and what was the other thing?
So you will say things like greater than or less than, positive or negative. That's the direction part. That will come from the test statistic in most cases, or just staring at the data. Like when we get to associations, we'll have indices that take on positive values or negative values, and so you'll know if it's a positive relationship or a negative relationship. The significantly or not significantly, that part is going into where is your result on this picture? Is it inside expected territory or is it outside? And where expected starts corresponds to the critical value that gives you where the area is. So a critical value of Z of 1.96 means that you would only find a result that is more positive than that 2.5% of the time. Sorry, you guys are backwards. More positive 2.5% of the time or more negative 2.5% of the time. So if you are inside expected territory, that's not significant. If you are outside expected territory, if your test statistic exceeds the critical value, then you are significant. Another way of saying that, much more directly, is the p-value. When you get your output, if you see this p-value is less than your alpha, is less than 0.05, it is significant. So the p-value is a sort of shortcut through all of this intermediate logic. It gives you the probability of getting that test statistic if the null hypothesis were true. That is what a p-value tells you. Okay, did that help?
Yes, thank you.
Okay, sure. All right, so we're up against the end of class. I think that's a good place to stop. So this is a univariate example. We're taking one sample mean and comparing it to a population mean. We'll do the same sort of thing, this null hypothesis significance testing, for measures of association and for other kinds of relationships between variables too. Like how likely is it that we'd get what we got if there really was no association in the population, if there really were no association, I should say. So this is your first chance to practice this logic, but it's going to come back over and over and over and over again in many forms. So, all right. So please work on formative assessment number 1 and get that to me by Monday night so I can look at the answers Tuesday, and we will go over it in class Tuesday.
we
Otherwise,
start and
let me know.
stop that? Is that formative assessment? Do we have to just sit down and go through it, or can it be starting? Can we come back to it?
You can certainly come back to it.
Okay.
The idea
Save a
is
lot of
that
delay.
you should be able to just answer the questions off the top of your head. And if
Okay.
you can't, then that guides you into where you need to review. So I'm not looking for an essay. I'm looking for like a couple sentences. You can write as much as you want to for your own benefit, but I'm not going to grade them. I'm just going to read them and give you credit for going through the process.
Thank you.
Sure. All right. Anything else before we adjourn? Okay. Thank you for being here. Thank you for listening. Have a good weekend. It's not garbage day, which means I say that. And I will see you all next week. Stay safe.
Thank you.